like to express my sincere gratitude for this kind of invitation to be here, and especially to Professor Magiram for his kind invitation. So let me share my presentation in order to start. So let us start now. Just check that everything is okay to you. You can see my slides.
Yes, sir. It's fine. You can start.
Thank you. So let me start. So we are going to talk about the reliability structure consisting of weighted components, an overview and some advances. So let us start by providing some main points of this talk. Some basic definition and necessary notations in the general field of reliability engineering will be provided first. Of course, the reliability structure with components with weights shall be our main aim of this talk. So first of all, we'll give the general motivation for studying such structures. Some well-known members of this class will be discussed briefly. And of course, an up-to-date presentation of the relevant literature will be also provided. Our main contribution shall be the development of a new member of this class called the consecutive weighted K1 and K2 out of n fail system. Its failure criteria, the failure criteria of this new member of this class will be described, while its reliability characteristics shall be studied in some detail. Of course, some research ideas for future potential will be discussed at the end of the presentation. So let us begin with some general definitions and basic notations in order to follow the next sections of this presentation. We denote by P1, P2, Pn the survival probabilities of the components of a system. We usually refer to them as reliabilities of the components. Their complementary probabilities are Q1, Q2, Qn, meaning that the failure probabilities of the components, or else their unreliabilities, are denoted by Q1, Q2, Qn. The reliability of the whole structure is denoted by R indexed by N of P1, P2, Pn. Ti is the lifetime of the I component of the structure, and let's begin by giving some simple examples of such systems. First of all, the K out of N, fail or good system, is a system which fails or respectively works if and only if the total number of failed or respectively working components is at least K. Some fundamental works on that system can be found in the papers of Barlow and Heidman in 1984 or FAM and on the Upadhyaya in 1988. Several recent advances on this topic are generated in the literature. Just indicatively, we refer to the paper of Kumar and Ram in 2022. A second member of this class is the consecutive K out of N fail systems, which fails if and only if there exist at least K failed consecutive components. Derman, Lieberman, and Ross in 1982 was the pioneer work for this topic, while recent advances can be found in papers of Daphnis, Macri, and Philippou in 2019 or Kumar, Singh, and Ram in 2019 too. Several generalizations of either K out of N or consecutive K out of N systems have been established in the relative literature. For instance, we refer to the R within consecutive K out of N fail structure, while several consecutive type structures with two failure criteria are also discussed in the literature. So, let us see the idea of weighted components. In a traditional setup of reliability applications, the components of a structure are supposed to be identical concerning their contribution to the operation of the system. That practically means that the weight of each unit is assumed to be equal. On the other hand, there exist several real-life applications where some components contribute more or contribute less than others. On such occasions, the failure of the underlying structure depends not only on which particular units have been already failed, but also depend on their individual contributions. These individual contributions, we shall refer to them from now on as weights of the components. Some intriguing application of systems with weighted components can be found in sliding window detection, in the field of quality or automotive control, and in sensor data fusion. Let us consider now a structure consisting of n components. Each component has its own positive integer valued weight, let's say Wi. The state of each component is denoted by xi for all I to up to n. Each component has its own reliability, Pi, and of course its complementary probability, Qi. Three classes of weighted structures will be discussed throughout the lines of the present work. The weighted K out of n systems with binary components, the multi-state weighted K out of n systems, and finally the consecutive weighted K out of n systems with binary components also. Let us start with the first one. The weighted K out of n good system works if and only if the cumulative weight of the working components is at least K. So, each component is either in a working state, in that case xi equals to 1, or has failed. In the second case, the variable xi is equal to 0. The weighted K out of n failed system now corresponds to the weighted W minus K plus 1 out of n failed system, where of course the parameter W equals to the sum of the weights of all components of the structure. The reliability of the weighted K out of n good systems satisfies the following recurrences provided by Wu and Chen in 1994. You can see that for running these recurrences, we need a set of necessary initial conditions which are provided at the bottom of this slide. In these initial conditions, you see that we need the reliabilities Rg of I, j for all j equal to 0 or negative values, and for all I equal to 0 too. So we see that we have Rg I, 0. We need in the initial conditions the Rg 0, j for all j, and of course we need the Rg I, j for all negative j. Let us see an illustrative example by running these recurrences. We aim, let's say, at determining the reliability of the weighted 5 out of 3 good system, consisting of components with weights 2, 6, and 4. In other words, the design parameters of our example are K equal to 5, N equal to 3, and the weights W1, W2, and W3 equal to 2, 6, and 4 respectively. So, our initial conditions are these you can see in the middle of the slide, so we are able to run the recurrence. Our first step is to compute the reliabilities Rg 1, j for all j 1, 2, 3, 4, and 5. You see that there are only 2 non-zero values. You see that the first 2 Rg values are equal to P1, while the rest are equal to 0. So we can proceed to the next step. Our next step is to compute the reliabilities of Rg of 2, j for all j again. Now we have 5 non-zero values. And finally, the last step is the determination of reliabilities Rg 3, j for all j 1 to 5. The last one, of course, is and corresponds to the reliability of the whole structure which was our target. So, there are also weighted K out of n good systems with 2 different types of binary components. let me say, first of all, that the failure criterion remains the same as before, but components now are classified into two groups. Let's say group 1, group 2, with respect to their weight and reliability. Each component of the same group has a common weight and a common reliability. We assume that M components belong to group A and have common reliability P1 and common weight W1. The remaining components belong to group 2 and have their own common reliability P2 and their own common weight W2. So the reliability of such structures has been given by Erelmaz and Sarikaya in 2014, and we can see the formula for computation of this reliability. Let me briefly refer to some further advances on this system. Mahmoudi and Meskat in 2020 extended the weighted K out of n good system consisting of two different types of binary components by assuming that the components within the same group can be non-identical. On the other hand, Franco, Tutuncu and Erelmaz in 2017 studied the case of such structures by adding a single cold standby component. Finally, Zhang in 2021 carried out a reliability analysis of weighted K out of n systems with heterogeneous components and random weights. Let us proceed to the second member of the weighted reliability structures. Now we shall recall the so-called multi-state weighted K out of n good systems. Each component and the whole structure now may be in m+1 possible states, which are denoted by 0, 1, 2, up to m. Each component has its own positive integer valued weight, W indexed by ij, for all I and j. The components do not share a common weight now, but also the weight of a specific component varies in terms of its state. We say that the system is in state j or above if the total utility of all components is greater than or equal to a predetermined threshold kj. We denote by P, indexed by ij, for all I and j, the probability that the I component of the multi-state weighted K out of n system is in state j, while their complementary probabilities, Qij, of course, correspond to the probability that each I component is in state below j. So, we denote by R, low indexed by j and upper indexed by capital I of nkj, the probability of the multi-state weighted K out of n good structure to be in state j or above. This probability of the multi-state system satisfies the recurrence you see in the middle of the slide. This formula has been provided by Li and Zhuo in 2008. Of course, a set of initial conditions are needed and provided by them. Some recent advances on this topic, you can see them at the bottom of this slide. So, let us proceed to the third one, the third member of the class of weighted reliability structures. Here, we refer to the so-called linear consecutive weighted K out of n systems with binary components. Now, we assume that the components are ordered in a line. Each component has its own positive integer valued weight, let's say Wi again. The total weight of the whole structure is given by the parameter W, and the state of each component is denoted by xi as before. We have the same idea. The component works or the component has failed. We have a binary component. Xi is equal to 1 if the component works, xi is equal to 0 if the component has failed. The linear consecutive weighted K out of n fail system fails if and only if the cumulative weight of some consecutive failed components is at least k. Now, the reliability of such systems is denoted by Rw of n, k, and if the system consists of independent components, then this reliability can be computed by the closed expression given by Erlmas and Tutunku in 2009 under the restrictions that the sum of all weights of all components of the structure does not exceed the quantity 2 multiplied by k. Here you can see that we need the determination of a function f of I, k, which is determined by the two branches given below. Just a brief note that for the reliability of these systems, some recurrences have been also developed by Wu and Chen in 1994. So, although the recursive algorithms can be used to compute the system reliability, their usage might be infeasible because of the complexity of computing time, especially for large systems, meaning that when the design parameters are quite large, then the computing time may be large too. So, a common way to overcome this drawback is to find a simple approximation formula for the reliability of the underlying structure. So, the reliability of the aforementioned structure, meaning the reliability Rw of n, k of the linear consecutive weighted k out of n fail system consisting of independent components, can be computed approximately by the following formula. Here we have, in fact, the fraction of these two products of functions, and we need the function g I, k given below, and we need the function f of I, k, which has been defined previously. So, we proceed to our main contribution. This is a new consecutive type weighted systems with binary components. Each component has its own positive integer value weight wi again. The total weight of the whole structure is given by w, while we have, again, in our framework, binary components, meaning that the variable xi is either 1 or 0 if the component works or has failed. So, the proposed structure is called consecutive weighted K1 and K2 out of n fail system and fails if and only if there exist. First, non-overlapping failed components with total weight at least equal to K1, and non-overlapping failed components, be careful, different from the ones involved to the first criterion, with total weight at least equal to K2. Let's see an illustration for giving a more clear, let's say, description of the new structure. Let us proceed to study the consecutive weighted 3 and 6 out of 5 fail system, consisting of independent components with weights W1, W2, W3, W4, and W5 equal to 2, 1, 3, 3, and 4 respectively. So, the resulting structure has the following design parameters: n equal to 5, k1 equal to 3, k2 equal to 6. And this structure fails if and only if there exist non-overlapping failed components with total weight at least equal to 3. This is the first failure criterion. And non-overlapping failed components different from the ones involved to the first criterion with total weight at least equal to 6. This is the second failure criterion. Just for illustration, we provide next two possible failure scenarios for the system, and you can see that the gray filled boxes indicate failed components, while the white ones indicate working components. Of course, it is easily observed that in both scenarios provided here, the resulting structure, meaning the consecutive weighted 3 and 6 out of 5 fail system, has failed, since the two failure criteria have been satisfied. We have met the failure criterion and the resulting structure has failed. So, to capture the operation of such a system, we first define the random variable Ti. Here, Ti is equal to the product of the weight Wi multiplied by the variable xi, which corresponds to the state of each component. The representation of the consecutive weighted K1 and K2 out of n failed system shall be actualized by the aid of an appropriate Markov chain. So, we first define the random variables d1, d2 up to dn as follows. You see that the di is equal to the di minus 1 plus ti whenever ti differs from 0, while the di variable equals to 0 whenever ti is also equals to 0. Of course, this holds true for all i2 up to n. Under the convention that the d indexed by 0, the d0 is equal to 0, and the weight w0 is also equal to 0, then the di variables could be equal to 0 if ti is 0, can be equal to wi if the variable ti minus I equals to 0, and simultaneously the variable ti differs from 0. The di variable could be equal to wi minus 1 plus wi if the ti minus 2 is equal to 0, while the next ones are not, meaning that the ti minus 1 and ti differs from 0. And so on. The fourth line of this idea goes as follows. The di equals to the sum of wi minus 2 plus wi minus 1 plus wi whenever the variable ti minus 3 is equal to 0 and the next ones are not, meaning that the ti minus 2, ti minus 1 and ti are not equal to 0. So we have the last, of course, line giving the more general form of this calculation. So the structure works if and only if either all d1, d2 up to dn are less than the maximum of the parameters k1 and k2, or exactly one di is equal to or greater than this maximum, and simultaneously the remaining ones are less than their corresponding minimum. In other words, the structure works if and only if the following ensue. The d1, the d2, the dn variable are less than this maximum already mentioned, the maximum of the design parameters k1 and k2, or we met one of the following scenarios already mentioned briefly before. So, given that the total weight of the structure, meaning given that the sum of the weights of all components of the structure is equal to or greater than the maximum of K1 and K2, then the reliability of these structures satisfy the following recurrence. So we managed to deduce these recurrence relations for the calculation of the reliability of the proposed structure. Finally, at the end of my presentation, some future potential. We may extend the present study to additional reliability characteristics of the underlying structures, such as the mean capacity loss between two successive time points, the component's importance measures, or the residual capacity of the system at specified time points. In fact, these ideas are already on their way. Of course, additionally, we may carry out a reliability study, a parallel reliability study of different classes of weighted consecutive type reliability structures. So, I would like to thank you all for your kind invitation and your kind attention. Of course, some references here are given for this present work. Thank you very much.